On behalf of UAF Summer Sessions and Lifelong Learning, I'd like to welcome those of you in the room, as well as those watching via live stream, to this evening's Discover Alaska lecture. At UAF, we acknowledge the Alaska Native Nations, upon whose ancestral lands our campuses reside. In Fairbanks, our Troth Yedda campus is located on the ancestral lands of the Dene people of the Lower Tanana River. Our speaker tonight is Don Hampton. He's a research associate professor of atmospheric and space science and optical science manager at UAF. He uses optical instruments to observe and study the aurora and upper atmosphere. The bad news is that he has COVID. He's doing okay. The good news is that he's still able to deliver his lecture via Zoom. At the end of this lecture, there will be time for questions and answers, and I will ask that you use the microphone when asking any of the questions so those watching from via live stream will be able to hear your question. And if you are Zooming right now, you can go to the website and go to uaf.edu/summer/events and scroll down to Wednesday's Discover Alaska, and you can type in your question as we're Zooming. The title of this lecture is Sunny with a Chance of Electron Precipitation, Space Weather and What It Means to You. Let's give him a warm welcome.
Great, thank you very much. Hope everybody can hear me. Let me pull up the presentation now. And if you can confirm that we're seeing the right presentation.
Looks good. Okay,
great, thanks. Yeah, so thanks for attending. And yeah, I wish I could be there with you, but I don't think it would be a good idea right now. So yeah, I'm feeling fine. Everything's good, but I just don't want to spread this around. Good, so yeah, sunny with a chance of electron precipitation. We'll talk about what all that means in a minute. That's important. Right now, I wish we had some real precipitation to dampen down some of the smoke and make things a little bit cooler for a few days. That would be nice. Yeah, I'm with the Geophysical Institute. I've been working on optical studies of aurora and other atmospheric science phenomena for over 30 years now. So I want to talk a little bit about what we're doing in terms of space research, and that now means space weather. I'll talk about that a bit. So, okay, so yeah, what is up with this space weather? Let's see. Here we go. There we go. Space weather. When I was in graduate school longer ago than I like to admit, we didn't really use the term space weather. We just said it was space research or auroral research or magnetospheric research. But in the last decade or a little bit longer, we've been starting to hear this term come up more often, called space weather. And it's now grown into sort of a research area, and it's also now got some legs in terms of governmental support. So there's now a journal called the Space Weather Quarterly. Canada and several other countries also have space weather groups as well. And there's a yearly conference or several yearly conferences talking about space weather specifically. And then during the Obama administration, there was a group that started a space weather strategy and action plan, and that actually was finally released in 2019. And there's now a group at NOAA, which is the same group that has the National Weather Service, now has a space weather prediction center as well, and that's located in Boulder, Colorado. So this is all now and sort of an official title for a research area. And so let's talk about what the U.S. initiative had. Like I said, there are international initiatives as well, but the U.S. initiative has this as its sort of action plan. It seeks to achieve 3 objectives, each supported by a set of high-level actions. We won't talk about details of that. To enhance the nation's preparedness for space weather events. So enhance the protection of national security, homeland security, commercial assets, and their operations against the effects of space weather. Develop and disseminate accurate and timely space weather characterization and forecast. Talk about that a little bit as well. And then plans and procedures to respond and recover from space weather events. So that's all, pretty dry stuff. What it really means, there are 2 main types of infrastructure that are really impacted with this. So it's satellites or objects that are in Earth orbit or beyond, and the power grid on the ground. those are both things that we are becoming more and more reliant on. And so what are the effects? Well, for satellites, the problem is you've got to communicate with the satellites for them to be useful. And so the space weather will affect that. And it also affects the upper atmosphere, and it changes the trajectories. So I'll talk about that a little bit. And then we'll also talk about this thing called geomagnetically induced currents, and how they possibly lead to power disruption, and how they have in the past, and hopefully we're prepared so they don't do so in the future. So where does space weather happen? Well, it happens anywhere in space, obviously. For what we are concerned about in terms of the research area of space weather, it happens anywhere between the sun and the Earth's upper atmosphere, really. So wherever space starts. And so here's a picture. I'll show some other versions of this picture with more stuff, but this has some like hashtags of some of the things that go on with space weather. Over on the left of the sun, we've got solar flares, coronal holes, coronal mass ejections, and some other different phenomena. In between the sun and the Earth, there's this stuff called solar wind, we'll talk about in a minute, and solar radiation storm. You've got other wavelengths of light than visible that come along and can affect us here on the Earth. And then when it gets to our magnetic field and starts affecting that, we get the things you see in there. We get aurora, we get a change in the ionosphere. We get things called total electron contents and scintillation and ground-induced occurrences I mentioned before. So it's this whole process from the sun to the Earth that's really what drives space weather and what space weather is all about. So we call it space weather, but I think a good question when discussing this is we need to think about, where does space really begin? Certainly there are companies now that will tell you that if you go to a certain height, you've been into space. But let's talk about a little bit where it happens here. So this is a plot. So in the vertical here, you've got the altitude above the ground in kilometers. So 100 kilometers, about 60 miles, and you can work it out from there. And then this is a logarithmic scale of particle density. So this is a million particles per cubic centimeter, and this is 10 million, and this is 100 million, and so on and so forth. So two things are going on. I'm showing here the total number of neutral particles versus altitude. And you can see as you go higher altitude, there are fewer particles. That's why it's harder to breathe when you get on top of Denali or whatever. And if you go up higher, it gets even lower. So one thing we know about space is there's not many oxygen molecules up there to breathe. And so we have trouble breathing up there. And on the left side, I'm also showing the number of charged particles as well. And so both of these things do something interesting, and it all does something interesting about 100 kilometers here. So typically we would all sort of agree that we, meaning the people in the space physics and space weather community, agree that 100 kilometers is about where space begins. You can still make some quibbles about maybe it's 110 or maybe it's 90 or something like that, but it's pretty close. So the thing that goes on is there's a thing called the ionosphere. It starts about there, so maybe a little lower. The ionosphere is where you get a significant number of charged particles, but you can see that really starts about 100 kilometers. And then you've got different regions in the ionosphere that we talk about. And then the neutral atmosphere is interesting as well. We define these areas by how the temperature acts with altitude. In the troposphere, the temperature goes down. If you're a mountain climber or been on top of a mountain, you can attest the fact that it's colder on top of the mountain than it is down in your car. So the temperature goes down. In the stratosphere, it goes back up again. The mesosphere goes back down, and then the thermosphere goes back up again. So it goes back and forth twice on the way up to space. And again, the mesosphere kind of ends at where space begins, and you get into the thermosphere, and we're dealing with the thermosphere when we're dealing with what happens with the neutral atmosphere in space. So there still is atmosphere in space. It's just very, very thin compared to what we have down here on the surface of the Earth. So the answer really is about 100 kilometers. So I said that everything sort of starts with the sun, and the big thing that really drives a lot of the space weather we deal with, excuse me, is something called the solar wind. And what it is, if you get up in the morning and pour your cup of tea or coffee and put it on the kitchen table and the sun's streaming through the window, what do you see coming off of the top of that cup of tea? Well, you see a little bit of steam coming off the top of that tea, and that's because the distribution of the particle motion in that hot liquid, there's enough, some of those particles, excuse me, have enough energy to come off the surface. Sorry, I don't know if this is COVID or maybe the the smoke as well. Excuse me. So the same thing happens with the sun. The sun is very hot, and so there's some particles that come off. The surprising thing is how many particles come off. I don't know if people know about scientific notation. Sorry, but this is 10 to the 36 particles per second. If you add all that up, that's about 6 billion tons per hour. Now, not everybody knows scientific notation, so there you go. That's how many zeros there are in 10 to the 36 particles. That's a lot of particles per second. They turn out to be, because the sun's mostly hydrogen, it's basically just charged particles split apart in a hydrogen atom, which means 1 electron and 1 proton. But the good news is, okay, even with 6 billion tons per hour, even over millions of years, we've still got millions of years or billions of years left in the sun. It's not going to go away. It's a big thing, and there are lots of particles in there. And so this wind is coming off. It's moving pretty fast. So typical values when it gets to Earth, the speed is 400 kilometers per second. That's about 240 miles per second. Notice that's not miles per hour. That's miles per second. So it's whipping along pretty fast. The density is very low, so it's about 4 particles per cubic centimeter. If you remember back to that plot I showed earlier, even in the upper atmosphere, our atmosphere is much more dense than that. So it's very, very wispy. And the magnetic field, most people don't know what a nanotesla is. I don't even know, but it's about 4 nanoteslas, where the Earth's field is about 60,000 nanoteslas. So it's very small compared to Earth's magnetic field, and that's why Earth's magnetic fields can sort of block it around, and that's what's shown in this picture here. So it's all driven by the solar wind, and to show why that's the case, I got a couple of demonstrations here. This is a movie that NASA put together a few years ago. They obviously didn't use Pixar or Industrial Light and Magic, but it still shows the same idea. This shows what happens when you have what's called a coronal mass ejection. So the solar wind's coming off sort of regularly all the time, but there are times when there's disturbances on the surface that sort of capture some of the solar wind for a while, and then it comes out as this big storm. And that's what's called a coronal mass ejection. So this is sort of an artist rendition of that. So here you go, the sun's boiling along, and all of a sudden here comes this coronal mass ejection, comes out, and in this case it happens to be aimed right at Earth. And so when it gets to Earth, it now sort of compresses our magnetic field on one side, throws some of that magnetic field on the other side, and that compresses down, and we get a process called reconnection, which then sort of takes the tension in that magnetic field and can sort of sling the particles back toward the Earth. So let me show that again. I'll go through that again. So again, there's the sun, here comes the coronal mass ejection. And now when it reaches the Earth, notice how the front sort of gets compressed. There you go. And it actually sort of strips off some of that magnetic field on the front, sort of throws it to the back, compresses it down, and now you get this sort of slingshot effect. And that's sort of what starts driving the energy. Now, this is not a very realistic simulation of what goes on. But the point is a lot of people think, oh, well, the aurora we see is directly from the solar wind. It's not. There are a lot of processes that go on between when this comes off of the sun and when it shows up in our upper atmosphere as an aurora. This just shows the fact that one thing that really drives that is this solar wind is actually a plasma. It's got charged particles in it. When you have charged particles moving around, which we'll talk about in a second, you get magnetic fields associated with that. And it turns out the orientation of that magnetic field really affects how it affects our Earth. So if the solar wind is southward, that's when you get this coupling to our magnetic field, like it showed in that movie, and you get that motion back in here. If it turns out to be northward facing, it bumps into our magnetic field and just kind of goes around it, and there's not as much interaction. So that's when we look at the solar wind, we're actually concerned about what the magnetic field looks like, but we'll get to that in a minute. So, that's an interesting movie. What I probably risking right here is I'm going to introduce people to what's called the Solar Dynamics Observatory. You can go to a website and you can download these just amazing movies of the sun going off. Here's what a coronal mass ejection really looks like. You get these areas, I think, would actually look like sunspots when you look in the visible. This is a wavelength we can't see by eye, but you can see what happens is something gets trapped there, and then something releases, and off it goes. And now that's carrying a big blob of particles. And if it's aimed toward Earth, then we're going to see probably really good aurora, or actually we'll see good aurora here for sure, but people down in Minnesota may be seeing aurora as well. So if you go look at the NASA Solar Dynamics Observatory, they got hours and hours of these movies, and I could sit there and watch it all day. But I think we need to keep moving along here. Here's another example. So that's the particles that come out, the physical particles, electrons and protons. And we know that light comes out because we get the sunlight every day. We know there's UV, we know there's some infrared in there because you can feel the heat. But there's also very, very short wavelength particles, very high energy photons or light particles that come out there as well. And these are X-rays and gamma rays, the same thing. X-rays are what you get, at a doctor's office. Gamma rays are even more energetic. Each particle can basically plow right through meters of Earth. And these can affect spacecraft, satellites. If they hit the wrong part of a satellite processor, that can take it down. But it also, a big rain of these particles can also ionize our upper atmosphere and change our ionospheric density. And you can actually see that in some movies of the density of the ionosphere later on. So again, the sun affects us in several ways. The solar wind is a big thing, but also just the output of these high energy particles can be affected as well. So let's go back and talk a little bit about that sort of process of the tearing of the magnetic field off the front. There's a lot of details here, but don't worry about that. Just remember when that came by, you could see the place where it sort of latched onto a magnetic field line and drug it back that way. Well, there's a guy back in the 18th and early 19th century named Michael Faraday, and if you found that if you change a magnetic field near a system that can measure that, it actually produces an electrical force. So the energy you put into changing that magnetic field, you can actually pick up in terms of a force, which we'd actually call a voltage. So here's that same picture we have with the sun on the left. The solar wind's going by, it's got a magnetic field, and it collects off there, and it sort of rolls that magnetic field across here. So you're changing that magnetic field in this region, and so it produces an electric force. And that electric force, now if you look from the top of the Earth, if you look at the sun this direction, and you map out the voltage across the ionosphere in this region, you can actually get things like 60,000 volts from this region. Whoops, sorry about that. 60,000 volts from this region over here to this region over here. So that's a lot. That's a large distance, so the voltage per meter is not that high, but certainly that's a large change in voltage across there. And that's certainly going to affect the charged particles in our ionosphere, in the upper atmosphere. And what that means is if you've got that, so you've got voltages and you've changed the conductivity of the ionosphere with the aurora, which I'll talk about in a minute, you create very strong currents. So if you put a battery across a wire, you get a current flowing through that. And the same thing happens when you've got electric fields or voltages, and you've got something that can carry them in the upper atmosphere called the ionosphere. That happens. So this current's very special for the aurora, and it's called an auroral electrojet. And strong events can actually create magnetic perturbations, and they're a few percent of the Earth's constant magnetic field. I mean, so the Earth has a pretty strong magnetic field, but this will actually locally change that quite a bit. So why does that matter? Well, how do you make that magnetic field? Well, you drive a current, and this is what we're talking about. These two guys, John Baptiste Biot and Felix Savart. John Baptiste looks like he had a hard day. Anyway, they came up with the fact that if you drive a current, you create a magnetic field. So that's what I was talking about earlier. So we run a set of magnetometers across Alaska just to measure these sorts of disturbances. And here's one from back March 18th, 2015, which is a nice strong storm. And so here's their three different components, the three different axes, north, south, and vertical, and then north, south, and east, west. And you can see something goes along, and if you watch the camera at this time, you probably saw the aurora really got bright, and you can see there are very strong changes in the magnetic field during that time. So these auroral electrojets cause these strong magnetic perturbations. Well, why does that matter to us on the ground? I mean, you and I probably can't feel a magnetic field perturbation directly. Well, what happens if another guy, the same guy, Faraday, said, well, if you change a magnetic field, right, and you have a large loop in there, it produces basically that electrical force or electrical current, right? And so that's the same thing that happens when you run a generator. If you have a magnetic field here and you spin a magnetic loop around there, you generate a little bit of electricity. That's how you run hydroelectric dams. That's how you drive or charge your battery in your automobile. But what happens on the ground if you've got an aurora going on and you had a very large basically electrical loop? Well, I can think of some electrical loops that might be affected by that, and that's a power grid. So what happens is you got these large changes in the magnetic field. They change fairly rapidly and they're very large, and you've got long metal basically lines running across the state or across a large area. Those can cause very strong voltages to show up in electrical lines. Now, the electrical lines we have are AC. The currents that are induced are more like DC. They don't change as rapidly as the AC in there. And there our transformers aren't really built to handle that. And so what happens is the transformers will heat up, or they will in other ways fail. And so this happened back in 1989. There was a very large storm, and one of these CMEs hit, and there's a very large storm. And the Quebec power system, one of their transformers failed. And once that transformer failed, the whole grid sort of collapsed because they couldn't readjust in time. Also turns out about the same time, the Toronto Stock Exchange had to halt because there was another stronger than the March storm. This is in August. It affected some microchips in the computer system as well. That was both the GIC and potentially even the gamma ray bursts. And this is something that happened from the March storm as well. This is in New Jersey. This shows some damage to one of the transformers as well. So certainly the power companies have learned their lesson from 1989, and I believe they've implemented a lot of safety protocols for taking care of that, because I really haven't heard of anything since that time. But it's a warning that if we had something even larger with very large changes or GICs, as we define down here, there could be problems with power grids as well. So what causes the light in the aurora? I've sort of bypassed that, but this is important for also talking about space weather as well. The light from the aurora is caused by energetic electrons from Earth's magnetosphere striking the atoms in the upper atmosphere. So we saw that sort of process of the magnetic field lines sort of snapping back, and that starts the process of driving these high energy electrons down to the upper atmosphere. When they hit atoms and molecules down in the atmosphere, they impart a little bit of energy into those, and what comes back out is very often a little bit of light that comes out called a photon. This process is actually very similar to that of a neon sign. In fact, it's almost exactly the same, just the energies are slightly different. And again, this happens in an interesting range between about 100 kilometers and 300 kilometers altitude. So again, there's that 100 kilometers. So a lot of things happen in this 100-kilometer range. It's very interesting. So 60 to 180 miles or so. So one thing we do in the work I do is we look at the different colors. I'm not going to spend much time looking at that because I really want to talk about space weather this time. But you can look at the different colors to see the aurora. And if you take the ratios of those, that'll actually tell you some of the energies going on. And so we use a lot of that on the ground now to supplement what satellites are telling us about how much energy that the aurora is producing. Okay, so I've talked a lot about magnetic fields, so I think it's time to show just a nice movie of the aurora. So we'll take a few seconds here and just breathe and enjoy this. So this was taken from the village of Venatai, about 120 miles north of here, or maybe a little bit further. This is back in 2017. The impressive thing is this is taken with a camera you can go off and buy, here in town, or if you order online, for less than $2,000. This is how amazing this explosion in consumer grade camera systems has become. The sensitivity of these cameras is just amazing. So this is real time. This is an aurora happening, sort of a little breakup arc, as we call it. So the thing that's going on, here's those particles coming down. They're making the light. The other thing I didn't mention in that figure as well is sometimes the energy is enough that they can actually strip off an electron off of one of those atoms or molecules in the upper atmosphere. And if they do that, Now they have an electron that's come off of there, and you've got a charged ion as well. And so that's what often creates an enhanced ionospheric layer here in the northern or southern regions in the auroras. So one way to see that is we've got, we can sort of estimate that from the optics. But the other way to see that is we've got several different instruments that can show that. One of those is a very sophisticated radar that we have out at Poker Flat called the Poker Flat Incoherent Scatter Radar. It's SRI International developed that and is operating out there as part of National Science Foundation. So the old incoherent scatter radars used to be these big dishes you had to sort of steer around. What you can see here is the new one has 4,096 individual antennas and receivers. And so it can actually do a thing called phase steering. It's a phased array, so you can actually change the time each of these emits its little packet, and you get different directions simultaneously. So these are different look directions from that antenna. And so this is the altitude here. This is the time of day, and each of these stripes shows an altitude profile of the number of charged particles in the upper atmosphere. So this is a way to look at that. And you can see during the daytime, you get charged particles up in the high altitude region, and that's just from the UV from the sun. But then the sun goes down. I can't remember what day this is, but it looks like it's a winter time. And then you get sort of lower altitude stuff. That might be some aurora, but certainly this stuff here at about 100 kilometers, that's aurora going on. And so you're rapidly changing, again, the number of charged particles in the ionosphere, especially in this sort of E region ionosphere, we call it, about 100 kilometers or so. So what does that mean? Well, one thing that does is that changes this region here from a good insulator, like a piece of glass, to a good conductor, like a piece of wire. And so that's a lot of times where that auroral electrojet happens. So it's the aurora that actually turns that on and off. So here's a movie. I can't help showing movies of my optic stuff. But here's an all sky camera that we have. And then here's some of those beams from the radar. And you'll see here in a second, the aurora will get a little bit brighter. And what I'm showing is the different colors here, showing the different densities, number of charged particles per a cubic centimeter or something like that. And you can see as the aurora goes by, it gets a little bit sort of yellower. It sort of goes back to green. And then here's going to be some exciting aurora in a second. It's coming up soon. Here we go. Now you can see when the aurora gets bright, everything goes red because now we've got a lot of charged particles in this range from about 95 to 125 kilometers. Oh, and by the way, that was where a rocket flew through all that as well. So we also measure things going on with these auroras and rockets. Well, so we saw already how this change in the conductivity affects the currents, and those currents can drive ground-induced currents, which might mess up power stations. But what else can it do? Well, here's an example of what you can do. So let's say you've got a satellite going over, sending out a signal, and you've got a ground station down here receiving that signal or hoping to receive that signal. If you have a layer here with different densities of charged particles, this starts to look like a lens. And so what you think is going directly from the satellite to the receiver might actually get deflected or slowed down or sped up. There are different ways of looking at it. But as you go through these structures, you might see something going on like that. So this was actually low latitude, and I'll describe why that's a problem. But here it was sending down a signal, it's just this quick brown fox jumped over this dog, and it would go through time. It would go through, and as it went through a structure here, it started losing track and was not able to send that signal, or the ground station was not able to receive that signal correctly because the signal was being deflected because of changes in that ionosphere. So it's like having a lens that you want to see a nice picture of what's going on, but it actually gets fuzzy because the lens is actually messing things up as it goes through. So that was low latitude at one frequency. The other thing is, if you look at GPS signals, we've got receivers here that can measure very detailed information about the GPS signal coming in and see when it gets delayed more than it should be or not. And we call that scintillation. So what I'm measuring or showing here is for one ground station, which is here at Poker Flat and just north of Fairbanks. Here are what we call the pierce points, the direction through which one of those satellites signal comes through the ionosphere on the way to the receiver on the ground. So here's satellite 14, it comes through there. This one doesn't seem to have a number, right? Or it's hidden behind there. It comes through there. Satellite 4 is over here, et cetera, et cetera. And you'll see these points move around a little bit. What we really see is the aurora will move around. And when the size of this crotch gets larger, that means you're getting more scintillation. So you're getting more disruption of that satellite, of that GPS signal as it comes to the ground. And you'll see how well that's correlated when the aurora goes by. So there's an arc that goes by, those two brighten up. So the arc goes away, it goes back to being sort of normal, moves down, and there you go. So this is something I think about every time I'm landing on an Alaska Airlines plane in Fairbanks, and I'm wondering if there's a really good aurora going on and hoping they're not landing on GPS. Well, it won't be a problem because the most GPS receivers, if they see that much scintillation, they actually drop that satellite. But as you saw there, sometimes it drops several satellites because several of them being affected at one time. Let's go back and show some of that early on stuff as well. So very rapid changes in the ionosphere around aurora can also affect signals in terms of GPS signal, which are very important, the GPS system is really reliant on the time that it gets there. And it's changing, it's delaying the time that the signal gets down to the ground. So that can be an effect. The other thing that when all these particles come down, they also heat up the ionosphere. It's you're dropping energy into the upper atmosphere. You drop some energy into something that one of the effects is also to heat it up. If we remember, if you heat up a gas, what does it do? Well, a gas wants to expand if you heat it up. And what happens is the upper atmosphere actually sort of expands and contracts as the aurora or one of these large storms happens. I love this picture. This is a website you can go to. It's the company that makes some of these GIS products for you. But they've gone through and they take a track of all of the satellites that they have coordinates for, and they plot them out at any one time. These are just still shots, but you can go to this side and you can actually watch it around. So here's a moved out view. You can see, or a wide view. You can see some of these geosynchronous satellites. They're out there and they're tracking the Earth as it goes around every 24 hours. But then you zoom in, you can see there's lots of things called low Earth orbiting satellites. They're 800 down to even 400 or 500 kilometers altitude. Well, why is that important? What does that have to do with space weather? Well, it turns out, like I said, if you heat up the atmosphere, you're going to change the density of that atmosphere. And so currents and active ultraviolet light from the sun can change that density, as well as active storms. So here we go. Here's a case where they measured daily data from a satellite at about 400 kilometers. I forget the satellite offhand, but they measured the density as they were flying along 400 kilometers, and that's the blue line here. And then they also did a simulation. The point of this paper was to do a simulation to see whether they could estimate it. They do a pretty good job. And then down here, this shows some of the parameters saying how active the sun was during that year of 2003, 2004. And you can see there's a period here where something really happened. This AP is kind of like the KP index you may have heard of before. And sure enough, when that went up way up, the density of the upper atmosphere changed quite a bit. Well, what does that mean? Well, if you've got a satellite flying through even a very, very thin atmosphere, if that atmosphere changes by a factor of 4, if you're driving down the highway and all of a sudden the air got denser by a factor of 4, you probably noticed that. Well, the satellites notice that too. It's very, very thin, but they're moving very, really fast. And the important thing is, because they're moving so fast, just a slight change in timing can make a big difference. So one example is, here's a prediction for a re-entry of a satellite. They knew it had run out of fuel and it was going to come in sometime. This is back in 2013 or so. But the prediction they had, based on all the factors they knew, said it was going to come down on this day. But the uncertainty was plus or minus 21 hours, and it takes about 90 minutes to go around. So this could basically, re-entry could come down anywhere. So this is just another illustration of what the impact is of not knowing how dense the upper atmosphere is, or not knowing how much it's going to change. Or the other way to put it is the importance of knowing how much it might be able to change, and maybe reducing this as well. So this is just when it was going to come down. But if you're thinking about two satellites that might be in the same altitude and might have a close flyby of each other, just an order of a few milliseconds might actually make the difference between an impact and not a heavy impact. So this is all very important. So there's a lot of satellite operators who want to have a better model of what's going on with the upper atmosphere. Okay, so I talk a lot about upper atmosphere, but it turns out lower latitude, there's some other things going on as well. This is not really related directly to aurora here in Alaska, but there's some dynamics near the equator that lead to regions of low and high ion density in the ionosphere. This is a little higher altitude. And again, radio communication is affected. This is that satellite track going over, sending that signal down there. This was the reason those signals were being affected. And so there are models to understand what's going on here. And with all sky imagers, you can sort of see what's going on if it's dark and clear, but we don't always have that. And they're still trying to understand exactly what's going on. This is affected somewhat by solar activity, but it's not directly affected by solar activity. So this is not really auroral activity. This is sort of electric fields associated with auroral or solar storms. So a lot of people ask, how do we predict when there's going to be space weather? And so just like terrestrial weather, it requires observations to be able to make predictions. We know if we don't know anything that's coming at all, we can't make any kind of predictions. But it turns out we really have one main source, unlike here for winds and temperatures and stuff like that, it comes from all over the other part of the earth. In this case, it's the sun that really drives all these things. So there are kind of three different time scales to contemplate when you're making space weather predictions. So one's called the solar cycle. I'll talk about that. And then there's a solar rotation. It goes around every 27 days. And then there's the time it takes the solar wind to arrive here at the earth to be able to make those predictions. So let's talk about a solar cycle. So over 11 years, the sun actually reverses its magnetic field orientation. So right now it's I don't know which way it is right now, to be honest, but let's say the magnetic field is pointing north now. It's going through a transition period over the next 8 or 9 years where we'll actually reverse and go south. And it actually doesn't flip over. What it actually does is sort of collapses, and when it collapses, it gets all those sunspots on the surface. And when you get all the sunspots on the surface, that's when you get those coronal mass ejections, and that's when you get sort of the most active aurora going on. And so that's what this shows, is the number of sunspots over the last 60 years or so. Here have been the last few cycles. Here's the 1958 cycle, which was a very large cycle. Sorry, I got one of these coughs going on. And then here's the last cycle, which was not actually that impressive in terms of sunspots. And here's the prediction for the next one based on what we've seen before. But the good news is, and this is a few months old now, is that some number of sunspots is actually going above the prediction. So I'm hoping we get a little bit more active solar cycle this time around. That's good for tourism here in Alaska, especially aurora tourism in the wintertime. That seems to be a pretty major economic driver now. So how can you use that? Well, obviously, during times like this, we're not going to get as many solar storms going on, but it doesn't mean there are no solar storms. In fact, the 1989, as we talked about, here's 1990. So here's a 1989. We were sort of coming out of a solar minimum at that time. So you can't exclude that there might be large storms in these, but certainly the number of storms you get on a daily basis is going to be higher during solar maximum. And here's another illustration of that. Also, it turns out it tends to be more solar active at solar max, but not exact correlation. In fact, there seems to be a little bit of a delay. There seems to be more activity. This KP is showing activity of aurora that seems to delay a little bit after the sunspot. But either way, you get sort of a cycle on 11 years. So we call that a solar cycle. We call it 11 year. It's really a 22 year, but it sort of modulated at every 11 years. We get more activity. So that's a long-term look. So if you're planning, if you're planning to go watch aurora, don't do it in 2032 because it's very likely we're going to be down at another solar minimum. The other one is the solar rotation. The sun rotates every 27 days or so. And so if we had a hot spot, say this hot spot here, that came by 18 days ago, and then if you wait 9 days later, it's likely to be active again. So again, if you look at plots of the parameters of the solar wind, and you sort of repeat them on a 27-day cycle, there seems to be a fairly good repetitiveness there. It's not absolute. Again, if you're waiting for CMEs, they happen sort of more randomly, and so it has to happen when it's pointing in a direction. But if there's something like a high-speed stream, there's some of these areas here that always have sort of high-speed solar wind coming by. And so if it goes around once, it's going to come around again, sort of like a sprinkler on a sprinkler on a lawn is going to come around again as well. So that's one way we do predictions of what's going to be good aurora. The one that probably we use the most here for doing rockets and doing sort of short-term studies is looking directly at the sun. There are a couple of satellites out there that are watching the sun all the time. This has a little block to actually block the sun itself, but you can see some of the particles, some of the emissions that come out from the particles around the sun. This is sort of the corona here. And then you can see there's coronal mass ejections coming out. There are several of these satellites in right orientation, so we can watch which direction they're coming. If they come directly at us, that's when we could start putting out warnings. We, meaning the Space Weather Prediction Center, can put out a warning saying, well, you should probably get ready. If you've got satellites, you might want to make precautions. So that it takes about 2 to 4 days for the particles from the sun to get here. So the solar wind takes, on average about 3 days, but sometimes it's faster, sometimes it's slower. And the other thing we can do is if you look at the gravitational effects of the sun and the earth, there's a region here called Lagrange point 1, where it sort of nulls out. And it turns out it's an easy place to sort of keep a spacecraft sort of in orbit there. It's a very small orbit locally. And that's about 1 million kilometers ahead of the Earth in the solar wind. And so if you've got that satellite out there measuring solar wind parameters, including the magnetic field, the density of the particles coming in, how fast they're coming in, and some other things as well, now you get to sort of see about an hour or so before it gets to our magnetosphere, what's going on with the solar wind. And certainly in terms of launching rockets or getting ready for doing special observations of the aurora, this is something we use all the time. We typically in the evening sort of see what the solar wind's doing, and if it's high speed and VZ seems to be south, we get ready, we pack our cups of coffee and our sandwiches and get ready to go out poker flat and get ready to launch a rocket. If it's all north and the sun speed is really low and the density is really low, then we get our YouTube subscription ready to go, and we sit and watch movies all night. So that kind of outlines the 3 different time frames that we look in terms of aurora. So there's 11-year cycle. There's about a 27-day sort of cycle. If it was good 27 days ago, it was good. One other thing I should mention, if you're interested in looking at the aurora and taking good measurements, you also sort of want all that to happen when the moon is down or at least not full or not, so there's sort of that in there as well in terms of doing that. And then on a daily basis or on a couple of day basis, we look at what's going on with the solar wind from the measurements for the coronal mass ejection and then directly from the solar wind for that evening. So let me summarize. I think I may have gone over a little bit, but we're getting pretty close. Space weather has potential to affect billions of dollars worth of infrastructure. So we've got lots of satellites up there. We've got lots of power grids out there. We affect the civil power grids, commercial and defense operations. All of those, I think we all rely on in large part. The main risk is really a big event. We've had largish events the last fine, and we've gone through those as well. But there was a large event back in 1859, just when people are starting to sort of understand what was going on with the space weather, called the Carrington event. It was probably an order of 100 times larger than anything we've seen in the modern era since like the Sputnik era. The only infrastructure back then was really telegraph lines, and there were people being shocked. There were sparks coming out of telegraph lines based on that, and those are not in northern latitudes. Those were like across Missouri or whatever. So probably very large currents flowing, and if that happened today, we're not sure exactly how that would affect both our communications and power grid distribution. So the main focus we do is trying to characterize a response both in the ionosphere and the upper atmosphere to one of these larger events and predict how infrastructure will respond. And it really is a global phenomenon, and therefore it's international enterprise. And we certainly work closely with our allies to make sure we understand what's going on and try to share as much data as possible. So it's a big topic. I know I threw lots of facts and figures and plots and stuff like that at you, but just to give you a sense of sort of the basis of why we do a lot of this stuff here at the GI and the whole space physics group across the United States. So with that, I will stop now and hopefully we have some questions.
Well, Don, I have one. How many people are working in your group, and how many satellites are you tracking?
So the space physics group of the GI, I think there are about 8 or 9 of us right now. It's gone through a couple of ups and downs, but I think we're still about 8 or 9 people, and we've got about 10 or 12 graduate students working on some of these projects as well. And then we collaborate with several other universities and several institutions across the United States. So it's the conference I was just at. There was somebody who was sort of new to that conference, and they were just really amazed at how well we all work along together, which is a nice thing. In terms of satellites, our group doesn't have any satellite. Our space physics group doesn't have any direct satellites right now, although we certainly use data from satellites that are making some of these measurements. So NASA has about 8 or 9 satellites right now that are doing sort of space weather kind of measurements, and several of our researchers will use that data directly. I'm more tied into the ground base, and so we've got the magnetometers I talked about. We've got cameras that we work. We've got some of these GPS receivers. We've got the radars out at Poker Flat and some other places as well. So the tracking the satellites, that's something that like NOAA and a couple of other companies, some companies do on a regular basis.
Are there any other questions from here?
Thank you. Keep it down lower. Okay, thank you. So when someone sends a satellite up into space, how do they purchase the spot where they orbit the Earth? And how do they pay for it, and who regulates it? How does that work? And can you actually see all of the satellites? So if, for instance, China or Russia or someone else sends a defense satellite, do they have any sort of Faraday cage, et cetera, that prevents it from being seen?
That's a great question. I wish I knew the answer to that. I believe there are international. I believe there are international agreements about how to parse out the space. I don't know who does it. I know that. So I can tell you one thing. You know, when we launch a rocket out of Poker Flat, we're on the line to NORAD, which is the U.S. Defense Department's group that sort of tracks what satellites and what space assets are up there, and so we have a communication directly with allies and potential adversaries saying we're going to launch a rocket. It's not a weapon. We're just going to launch the rocket. So there are international agreements. I unfortunately I don't know all the mechanisms because they don't let me touch rockets or launch satellites myself. So I don't get to do that stuff. But yeah, I believe there are international agreements on how they parse it up. I'm sure the large companies have to pay a fair amount of money, but I don't know who they pay that to in order to do that. So sorry.
Thank you. No worries.
Anyone else?
Regarding the James Webb Telescope at the L2, is it kind of naturally safe there from all of these things you've talked about, or is it still capable of sustaining damage?
So yeah, so it's L2. Let's see, here we go. L2. It's beyond the moon. So the answer is no. It's still affected by the solar wind directly. What it's really susceptible to out there are these very high energy particles I talked to, the gamma rays and high energy protons and stuff like that. So it was built to specifications in order to be able to handle that kind of stuff. The reason satellites are so expensive is because you have to build parts or purchase parts and put together redundant computer systems so that if you do have what's called a latch up, if you hit the wrong bit at the wrong time, the computer doesn't just give up and everything goes to sleep. And then you shield things so that the impact of a particle might be less in there. So no, at L2 it's not really shielded. It is somewhat shielded because it kind of goes behind the Earth. This is not to scale, obviously, but it does kind of go behind the Earth and goes to the magnetosphere, which helps a little bit. I didn't really mention kind of the worst place to go through is actually our radiation belts, which are fairly close to Earth, but the James Webb will not be affected by that. That answer your question?
Yes, I would like you to talk a little bit more about, you said the big event or a big event, and you gave an example of the Carrington event. But so what was that? And briefly, like, so in what way was space weather the cause?
Well, so as far as I remember, it was just a very large coronal mass ejection, like one you see here. It was just the density. I think, if I remember correctly, it was actually like 2 or 3 coronal mass ejections, is what people have speculated. It's just that the number of particles, the speed at which they came, and the orientation of the magnetic field were such that it just drove the magnetosphere in a way that we really haven't seen in there. And it basically just was like a flood of solar wind when we're usually expecting just sort of a stream going by. So it's basically a flood event, and that just drove the effects I talked about, which are the change in the ionosphere, the currents flowing up there that would affect power grids now. It's just a matter of magnitude from what we've seen before. Luckily, the really large storms happen a lot less often. It's like a 1,000-year event. The smaller storms happen more often.
Any other questions? Well, we would like to thank you very, very much for this incredible lecture. And I hope you're feeling better. Hope you're
Thank you.
feeling better.
Feel pretty good. Thank you.
And I would just like to mention that there are more Discover Alaska lectures coming out. The next one is on the 13th, and it's with Kathy Cahill, and it's about drones in Alaska. So that should be really, really fun. So thanks so much. Let's give him a round of applause.
Thank you.